Cultural and identity attractors. Welcome to part 3 of the Chaos Theory series. We're with your host and narrator and teacher, professor and enseignant, Christophe Bedard. And let us get on to more chaos with what we call cultural and identity attractors. The cultural equivalent of attractors would be chiefs, tribes, states, and what gives us identity, like religion, class, and worldviews. Chaotic attractors. Now there is a class of attractors that are a bit out of the ordinary. They are known as chaotic or strange attractors. They consist of infinite numbers of curves, surfaces, or higher dimensional manifolds. They are in fact fractal objects. The strange attractors live in a mathematical construct known as phase space. Phase space is an imaginary space. It is a way in which numbers can be turned into pictures, making a flexible map of all the information available. Let's define phase space. The representation of phase space. We are familiar with architectural drawings that represent a three-dimensional building in a two-dimensional plane. But suppose instead of a fixed object, a building, we have a moving object, say a pendulum. We can represent the horizontal and vertical motion of the pendulum in a two-dimensional graph. The horizontal axis and the vertical axis provide information about where the pendulum is. Similarly, phase space represents the state of an object in a multi-dimensional plane. The motion of the simple pendulum could be shown on a graph where the x-axis is the angle of displacement from the vertical and the y-axis is the angular velocity. On this phase space diagram, the simple pendulum shows as a circle. Phase space turns dull statistical data into a telling picture, abstracting all the essential information from the moving parts and providing us with an easy-to-grasp overview of the system's behavior over time. In a phase space, the complete state of knowledge about a dynamical system at a single instant in time collapses to a point. That point then is the dynamical system at that instant. At the next instant, the system will have changed, and so the point moves. Phase space makes a dynamic system easy to watch. It is the image that a fly moving around a room. It is the image that a fly moving around the room would have a changing system. Okay. So we're talking about steady flowing stream, periodic flowing streams, and quasi-periodic flowing streams, right? What is strange about strange attractors? First, they look strange. A multi-dimensional multi-dimensional imaginary object is bound to look strange. Second, the motion on the strange attractors has sensitive dependence on initial conditions. Third, strange attractors reconcile contradictory effects. A, they are attractors, which means that nearby trajectories converge on them. And B, they exhibit sensitive dependence on initial conditions, which means that trajectories initially close together on the attractors diverge rapidly. Fourth, and this is the tricky bit, while strange attractors exist in an infinite dimensional space, the phase space, they themselves have only finite dimensions. The Lorentz attractor. The most famous strange attractor is known as the Lorentz attractor because it was first discovered by Lorentz. This is what it looks like. The term strange attractor was coined by David Rouel, professor of theoretical physics at the Institut des Hautes Études Scientifiques à Bure-sur-Yvette, en France. He introduced the term in the early 70s in a paper written with a colleague in which he proposed that fluid turbulence is an example of chaos. There have been objections to the term strange attractor. For example, the Russian mathematicians Boris Chirikov and Felix Israelov suggest that strange attractors look strange only to a stranger. So the predisposition, it's in fact kind of reinforcing the material or socio-material conditions of the apparition of a strange attractor, is precisely that in knowing what it is, or in understanding it, apprehending it, maybe comprehending it, the quality of strangeness must disappear in the process of comprehension and perception. I think that's what the Russian mathematicians were trying to imply with the phenomenon of strangeness. However conforming it is to the material, and however the social realm conforms to materiality in the sense of our intellect, I think explains why we would further, if strange attractors would remain something important, that we would further try to understand it by its relationship to ascertainment. So let us continue. These infinitely complex patterns of curves and surfaces are exactly what we should expect, even though rather few folks actually expected them. However, the name is too attractive for most scientists, and the term has stuck. The strange attractors have fueled the fire of chaos theory. Researchers now look everywhere for strange attractors in any system that appears to be acting randomly. The butterfly effect. Lorentz is also associated with the idea of the butterfly effect. In 1972, he presented a paper at a conference in Washington entitled, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" Let me repeat this. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? He did not actually answer the question. He did note, however, that if a single flap of a wing could generate a tornado, then it could also prevent a tornado. Moreover, a single flap would not have more or less effect than any other flap of any other butterfly's wings. And see here the applicability of the pattern of the strange attractor is kind of imbricated in the wing structure of the butterfly. And so you can understand potentially the interrelationship between strange attractors and the butterfly effect in its causal reverberation. However, in the end, how it relates to the process of attraction remains to to be associated with the causal effectivity of the butterfly effect in and of itself. The book might answer these questions as we move further along. Two factors ensured that the butterfly effect would become an emblem of chaos. First, amongst the earliest chaotic systems studied by Lorenz was the famous strange attractor that resembled a butterfly. It was natural for some people to assume that the butterfly effect was named after this attractor. Second, the butterfly effect was given a mythical status by James Glake in his best-selling book Chaos in 1988. The butterfly effect makes the point that initial conditions and small perturbation are very important in chaos. In A Sound of Thunder, a short story by Ray Bradbury, the death of a prehistoric butterfly changes the outcome of a present-day presidential election. David Ruel. Mathematical physicist David Ruel gave chaos theory a kickstart with his work on turbulence. For decades, turbulence had been a major problem for scientists. Werner Heisenberg, 1901 to 1976, who contributed to the uncertainty principle, found in quantum physics, probably still worried about it even on his deathbed. The uncertainty principle. My own contention with the uncertainty principle is that it is more related to our incapacity to measure a moment without collapsing it into a time, a condensation of time, right? So it has to be, which makes so that any measurement made about a quantum event has to encapsulate it in a finite amount of time, which will relativize the position and the momentum of whatever is being observed at the quantum level. So the uncertainty comes from the precision of the capture versus, so it says the more you know the position, the less you know the momentum. And that's precisely because the length of the capture of the event will then vary the position into a trajectory, right? So the trajectory might be understood as continuous, and at this point, our observation apparatus does account for the continuous position and velocity of a quantum event, but only at a certain level of size. And the further you dive in the collapse of it, the truer it becomes again, meaning the uncertainty principle becomes again onto the quantum event in need of being apperceived or perceived in the first place, right? And so once you arrive at that conclusion, then you understand why Heisenberg spent his whole life trying to decipherate exactly how we could identify quantum events. Not only identify it, observe them in contingently continuous ways, and then represent them, right? I don't think he had the full picture of particle physics as it exists now at Triumph and at CERN and at other facilities. I think Heisenberg would have only dreamed to imagine what we have now in our capacity to achieve, like what we have now in order to achieve what he perceived to be something valuable at his point in time in life. And in 1976, the computer was already invented and blah, blah. So he was well on his way in theorizing the exact extent of material reality as it was experimentally corroborated by more and more complex machines of operations, including computers, including detectors, including what you would call like these accelerators, right? Based on millions of dollars of resources agglomerated with specific physical functions which allow for the observation of quantum phenomenons, quantic, atomic, and subatomic, precisely what we call a particle. And so once you arrive at the particle level, then what you're looking for is some corroboration of evidence as to our theory, so that we are sure that the theory we have about material reality conforms to an observable phenomenon. And that observable phenomenon is corroborated through highly specific and specialized technological machines, which mimics proper observation through further corroboration of our understanding of materiality. Right? So there's this sense of self-confirmation of the process, which is also skeptically and inquisitively approached, in the sense of always putting into question what will allow for the observation of a certain phenomenon. And again, the self-confirmation of the process is what's interesting, because we are looking for the materials which will produce the observational reaction necessary to then confirm the phenomenon, right? So the self-confirmation is only there to further reinstate that what we are trying to do is to confirm our mind onto material reality. And to deny the zones of the mind applicability to materiality when it should not be applied. So there's a form of exclusion of knowledge which is formed in the process of in the entire process of particle physics as an endeavor of understanding towards material reality. And so I think with this overview, you might have a better sense of where we stand in terms of applying chaos theory to microsystems and then onwards to macrosystems, right? And materiality is one of the things which can be systematized, functionalized, and mathematically objectified in order to, well, for a multiplicity of purposes, including redistribution. And so let us continue with what is turbulence, right? So the flight has been tough on this one. I think a lot of considerations have to be made in order to understand how you would participate in these societal and scientific functions, or even have a grasp of what it proposes. Hence the necessity for further studies accompanied with these videos that I'm making, because ultimately all the knowledge will never be accessible through one source. And so, on that note, let us continue on what is turbulence. You can see turbulence in action by making a quick visit to the bathroom. Open the tap by a very small amount, gently, and you can arrange a steady stream of water between the tap and the sink. The column of water seems as if motionless, but of course the tap is running. If you open the tap a little more carefully, you may be able to arrange regular pulsations of the water column. This is periodic motion. When the tap is open a little further, the pulsations become irregular. Finally, when the tap is wide open, you have a total mess. Very irregular flow. This is turbulence. How does turbulence happen? Turbulence is a mess of disorder at all scales. It is unstable and highly dissipative, meaning that it drains energy and creates drag. The puzzle is, how does a smooth, stable flow become turbulent? How does a plume of cigarette smoke flowing smoothly upwards suddenly break into various smoky streaks? Rouel's approach. The equations of fluid flow are in fact mostly impossible to solve. They are nonlinear partial differential equations. Rouel decided he would try to work out an abstract alternative to the usual approach. X describes a fluid in turbulent motion as quasi-periodic functions of time. I suggest that three independent motions cause all the complexities of turbulence. Rouelle published his analysis in 1971 in a paper entitled On the Nature of Turbulence, co-written with Floris Takens, a Dutch mathematician. Actually, Rouelle was an editor of the journal, and he accepted the paper himself for publication. This is not a recommended procedure in general, but he felt it was justified in this particular case. Even though much of the mathematics in Rouelle's paper was obscure or simply wrong, it contained elements that made a lasting impression. Turbulent flow is not described, as generally assumed, by superpositions of many modes, but by strange attractors. His use of the term strange attractor proved to be decisive. And so, what he's proposing here is turbulence is not just some interference between signals. It's in fact a phenomenon caused by the existence of the strange attractor as described by Lorentz. And Rouelle came and confirmed the applicability of the strange attractors to turbulence. New questions arose. How could an infinite number of loops and spirals be contained within finite space? How can so much be going on in such a tiny space? Why infinite logic to understand what a point in time is going to do? Rouelle suspected that the visible patterns in turbulent flow that come and go at random must be related to some laws that had not yet been discovered. One thing that was known about turbulence was that a broad spectrum of cycles was present at once. But how could this be represented? Could it arise from simple equations? The attractor would have to be stable and represent the final state of the dynamic system. It would also have to be non-periodic, never repeating itself and never cutting across itself. To produce every rhythm, it would have to be infinitely long within a finite space, a fractal. But the term strange attractor was not then known. Rouelle argued that such a thing had to exist. He was vindicated when strange attractors began to appear as far apart as Germany and Japan. Robert May and animal populations. Robert May, 1936. An Australian mathematical biologist who worked at Princeton University and later became Royal Society Research Professor at Oxford University, was responsible for pioneering work in population dynamics that helped shape chaos theory. I studied predator-prey populations and found that nonlinear feedback forces in the environment produce pseudo-random changes in animal population. Let me repeat that. I studied predator-prey populations and found that non-linear feedback forces in the environment produced pseudo-random changes in animal population. Okay. Here is something that has been found, right? The population of the particular species, say antelopes, varies from year to year, and the total number in a particular year provides a good indication for numbers during the next year. Unlike the pendulum or a ball on a snooker table, animal populations do not have my Newton's law. The conventional wisdom said that usually the population would fluctuate around a point, with predators, food supply, the environment, and disease all keeping the numbers in check. Thus, if a population rose above a particular level, food supplies would dwindle, more of the animals would starve and die, and then the population would return to its normal state. The year with the largest population would therefore follow a year with medium-sized population. May's bifurcations. In the 1970s, May's research revealed that the equations used to describe fluctuations in animal populations were more complicated than they appeared to be at first sight. He discovered that, with the parameter at high levels, the system would break apart and the population would oscillate between two alternating values. Ecologists had previously studied these equations, but they were looking for constants and ignored the information contained in the graphs. May and his colleagues looked at the graph and realized the wider implications. I was looking at the equations at all at once, as a whole, not at points on the graph as had been done before. Okay, so he was looking at the entirety of the graph and not at a specific particular point of the graph. May described his discovery as the snake in the mathematical graphs, and the alterations were dubbed bifurcations. As we have already seen on page 18, his work confirmed the idea that biological systems are governed by non-linear mechanisms. Chaos in real-life events. May observe that in the laboratory, animal populations do not behave chaotically. They actually fluctuate around a point according to environmental factors. They are linear. But this does not mirror what happens in the real world where populations experience the periodic doubling. The answer to predicting animal populations lies within computers, where in an imaginary world, the investigator can stipulate all the factors that could impinge on an animal's life. Environmental randomness is introduced too, for example, by altering the numbers of eggs laid by an insect. Though this is interesting, it does not totally cover all real-life events. Species interact with each other, and we can never know all the factors affecting one group of animals. Or as May says, there is unfortunately no punchline to this part of the story. Mitchell Feigenbaum, Nonlinear Patterns. Mitchell Feigenbaum, a graduate student at Massachusetts Institute of Technology, MIT, was the first to prove that chaos is not a quirk in mathematics, but a universal property of nonlinear feedback systems. He provided the first significant theoretical evidence that chaos exists in many real-world situations. During my research, I noticed that a certain pattern carried over from one nonlinear system to another. It was the limit of a sequence of numbers that appeared in the calculations. On my hand calculator, the special number was 4.669. Feigenbaum consulted his colleagues, who advised him to check his results using larger data and a computer. The computer gave a number of 4.669201690. This convinced Feigenbaum that something was afoot. Imagine that a prehistoric zoologist decides that some things are heavier than others. They have some abstract quality he calls weight, and he wants to investigate this idea scientifically. He has never actually measured weight, but he thinks he has some understanding of the idea. He looks at big snakes and little snakes, big bears and little bears, and he guesses that the weight of these animals might have some relationship to their size. He builds a scale and starts weighing snakes. To his astonishment, every snake weighs the same. To his consternation, every bear weighs the same too. And to his further amazement, bears weigh the same as snakes. They all weigh 4.669201690. Clearly, weight is not what he supposed. The whole concept requires rethinking. Gleich Chaos, page 174. Easy solutions to difficult problems. Feigenbaum had no idea why the irregularity occurred. He assumed that his numerical functions expressed natural laws about systems at the point of transition between order and turbulence. Patterns in numbers implied patterns in turbulence. He eventually explained his discovery by coining the notion of universality. It did not explain the phenomenon, but did make a difference between beautiful mathematics and useful theory. Universality suggests that by solving an easy problem, physicists can solve much harder problems. The answer will be the same. It also means that different systems will behave identically. This was hard for physicists to swallow, for they have always believed that difficult problems require difficult solutions. So it took the scientific community some time and tribulation to accept Feigenbaum's discovery. Starting the next lecture, we will discuss Ilya Prigogine and the idea of dissipative systems, so that we may further engross ourselves in the chaotic pattern of understanding, which is chaos theory, so as to further understand order in its utmost form